If you've taken only a single calculus class before, chances are you've discovered what a derivative is. It's just the slope of a single variable function. We'll need to extend that concept a little bit here to multivariable functions. But the extension is not very hard. What we need to define a partial derivative. And a partial derivative is simply the same thing that you already know as a derivative, only it happens along a slice of a multivariable function. We'll illustrate this here. Take, for instance, the utility function x1 to the 1/2, x2 to the 1/2, which is graphed out here. You can see what this function looks like as we rotate it around. It's simply a hollow mountain without a peak, as our utility functions tend to be when we assume more is better. Now suppose that we hold the x1 good fixed at 4 units, and we define a new function that's the vertical slice of our original utility function, holding x1 fixed at 4. This new function can mathematically be expressed as a function v that's now simply a function of the x2 good, because we've set the x1 good equal to 4. So we get v of x2 is equal to 2 times x2 to the 1/2, because when we substitute the 4 in for x1, we get 4 to the 1/2, which is equal to 2. And if you know how to take the derivative of a single variable function, you know how to take the derivative of the v function, because it's a function of only a single variable, x2. So the derivative of v with respect to x, or with respect to x2, is simply equal to x2 to the minus 1/2. That's the slope of the slice that we've extracted from the original utility function when we held x1 equal to 4. This is also called the partial derivative of the original function u with respect to x2 evaluated where x1 is equal to 4. We can therefore think of a partial derivative of a function of two variables as the slope, or the derivative, of a single variable function that's created when we hold one of the variables fixed. So far, we found the slope of a vertical slice of the utility function by simply plugging in the value 4 for x1, creating a function of a single variable, x2, and taking the derivative. More generally, without substituting a specific value in for x1, we could simply treat the utility function u as a function of a single variable x2 by treating x1 as a parameter. When we then take the partial derivative of u with respect to x2, we can treat the x1 to the 1/2 term as if it was just some term a, for instance. So as we take the derivative with respect to x2, we take the exponent of x2, 1/2, times x1 to the 1/2, which we just treat as a parameter, times x2 to the minus 1/2, just as if we took a derivative of a single variable function that's a function of x2. We can then evaluate this partial derivative for different values of x1. So if we set x1 equal to 4, for instance, we're again operating on the slice where we've held x1 equal to 4, which is the function v equal to 2x2 to the 1/2. Before, we already found the slope of this function to be the derivative of v with respect to x, which was equal to x2 to the minus 1/2. We can now find that same slope by using our general expression for the partial derivative of u with respect to x2. Our expression that says that that partial derivative is equal to 1/2 times x1 to the 1/2 times x2 to the minus 1/2. Just plug x1 equal to 4 into this equation, and we get 4 to the 1/2, which is equal to 2, times 1/2 gives us just 1, so all we're left with is x2 to the minus 1/2. The bottom line is that taking a partial derivative is no harder than taking a derivative, because a partial derivative, when all is said and done, is simply the derivative of a vertical slice of a function of multiple variables. The mechanics of this are pretty simple too. If you have a function of multiple variables and you're taking the partial derivative with respect to one of those variables, Simply treat all the other variables as if they were fixed parameters in your equation, and then take a derivative. Remember, a partial derivative is just a derivative of a single variable function, because once we hold all the other variables fixed, we are left with just a single variable function.